Hello everybody, I'm your host Hal Curtis and I'd like to welcome you to The Space Industry by satsearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello and welcome to today's episode of the Space Industry Podcast by satsearch. I'm joined today by Adrian and Michael from Texas Instruments. Texas Instruments is a company that I'm sure you've heard of, especially if you're in our industry. And today we're going to be discussing how to optimize data acquisition systems in space applications. Quite a technical topic that I think has a lot of applicability to missions and systems of all sizes. So firstly, Michael and Adrian, thank you very much for being here today. I wondered if you could just explain what you do at the company.
Yes, hello, and thanks for having us here, Hal. Yeah, I'm Michael Seidl. I'm a systems engineer in the Systems Engineering and Marketing Group, and our team is in particular responsible for the aerospace and defense market sector.
Hello, everybody. I'm Adrian Helwig. I'm field application engineer, and I'm supporting space customers in Europe.
Excellent. That's great. Thank you, guys. So, okay, let's get into this, the topic today of optimizing data acquisition systems. Now, Earth observation applications, as we know, are kind of driving up the requirements on components because they need higher data rates. And as always in space, they're looking for low power consumption and smaller physical footprints. Even when there are large optical instruments with large apertures, other aspects of the entire system, they still want to minimize the physical size. Every satellite has complex requirements in terms of telemetry, as we know, as defined by the nature of space. But what are the compromises that you see designers facing when it comes to developing, solutions for data acquisition systems? Where are the trade-offs that have to be made, or what limits are we seeing in the industry today?
I think the very fundamental decision criteria is really the radiation hardness level. That probably comes before we look at size, weight, and power and cost. And the radiation hardness levels is where many of the customers or many designs really are focused towards the higher Earth orbits or geostationary orbit or deep space missions. And this is where there's typically no room for compromise at all for designers and just have to pick the so-called QMLV RHA products, even though they are very expensive and there's also limited choices they can do there. Now, for the low Earth orbit, also called the LEO missions, there is indeed the opportunity to go with something that is lower in radiation hardness. And here, of course, still the commercial off-the-shelf devices are still not a good choice in such applications, unless the day in the orbit is planned for a very short period and the total cost of the satellite allows you even for a potential loss of it. So for LEO missions, designers then typically prefer the so-called radiation-tolerant products over the more expensive radiation-hardened products. Still, it's not that trivial also in the low orbits, right? The satellites operating in the low Earth orbits, they fly a lot faster than the Earth rotation and pass multiple times per day from full exposure to the sun into the cold shadow side of the Earth and back. And this is where the commercial off-the-shelf devices are simply not made for such extreme and permanent temperature cycling, right? And then also, like, of course, in LEO, you have lower radiation levels than in the GEO areas, but still, right, when you compare this to Earth, on Earth, you have really the full protection or a lot of protection from the magnetic Earth field and from the atmosphere. That is in the LEO space not the case that much. And this is where radiation tolerant devices really are still required. And this is where TI offers here also a classification called the Space Enhanced Plastics, or SEP in short. So that was now the very general answer and is applicable to any type of design.
Yes, Michael. So this was general, but I think it does also apply for the data acquisition system, right?
Yes, of course, right. It's like for any design. So, but you're right. Let's look into the specifics of the data acquisition design itself. So for the data acquisition circuit, designers do typically start with defining their requirements for the analog to digital converter, as this is typically the most expensive and also the most power hungry device in the data acquisition system. And especially for telemetry and health monitoring, satellites typically require a very high number of signals to be monitored. And in order now to avoid that each signal requires its own ADC, designers to typically add multiplexers. And in many cases, such multiplexers are already integrated into the ADC. So for example, at TI, our 12-bit ADC, the ADS128S102-SP, comes with an integrated 8-channel multiplexer and it is really very popular in such applications.
Right, fantastic. Thanks. That's a really good introduction. I just wanted to say quickly for the listeners, you don't need to remember ADS128S102-SP. Okay, we will include these in the show notes of the episode, and on the satsearch blog, we'll also link to any of the products mentioned by name, and so you can see the product page. Don't wear out your pencil writing down the codes. But yeah, so. As I mentioned, this is a really good overview of the overall kind of data acquisition needs of the system, and especially explaining the needs of the ADC. But what about the rest of the signal chain itself?
Well, yes, that's also a very interesting topic, and I think designers needs to consider here a very different cases, right? So. And in our portfolio, we have a lot of products, different products, very well known for various reasons. So let me give you an example, like the OPA 4277 is very well known device because it has a very wide supply range, very good signal conditioning performance, and also very low offset voltage and drift, right? Another example could be the LMP7704. This is again a very good choice when interfacing precision sensors with high output impedance. And this device, for example, offers ultra low bias of plus minus 500 femtoamps. And it can also be used for different configurations like transducers, bridge configuration, stray gauge, and even transimpedance amplification.
Yes, Adrian, fully agree. The LMP7704 is indeed a great choice for a lot of cases. But let me bring, in contrary to the LMP7704, there are also amplifiers that are very specific to a single use case, maybe such like a shunt current sensing, right? For example, there is a dedicated current sensing amplifier available from TI called ENA 240. And this device really comes with very great PWM rejection, has a very wide common voltage range of minus 4 volt up to 80 volt. And it also comes with a high gain of 20 and still a maximum gain area of only 0.2%.
Okay, yes, thanks, Michael. I fully agree with you. So already for a topic of a sensor interface, there are already a lot of choices to be made, right? So, but let me talk about something else here. During the operation of the satellite, there are situations where a supply voltage or current level can rise too fast, right? And this could destroy the complete system. So if we now look at the classical approach out there, like an ADC and MCU integrated into the signal chain, those systems are often too slow for such a cases. So designers are forced to implement a comparator in the analog domain to handle those kind of situations, right? And if we look at our portfolio, we have a space-grade comparator, TLV1704. This device offers you ray-to-rail input, also very low propagation delay of only 560 nanoseconds, and very wide supply voltage range of 36 volts, and this regardless of the supply voltage. So with this device, customers are really very flexible to handle almost every application.
What are the sort of bottlenecks that you see designers facing in areas such as, with observation applications when it comes to applications like the telemetry system?
Yeah, that's a very good question. Well, there are several aspects of those challenges. And I can mention maybe two of them. On the one hand side, the achievable technical performance of the system is very important. But on the other side, there is also adaptability to different orbit requirements. This means LEO or GEO constellations and their radiation requirements. So if we now talk about the technical performance, when designers are thinking about data acquisition systems, they always need to fulfill some kind of SNR performance of this system, right? And this is because the data acquisition system is obviously the heart of the whole system. And now, because the final resolution of the ADC also depends on several other factors like clock jitter, reference voltage accuracy, input stage configuration, power supply rejection ratio, all those aspects needs to be considered during design process. If we look now at the specific products, for example, if you have an application where 12-bit resolution is sufficient, we can offer our very well-known ADC 128S102, which is very well-known 12-bit 8-channel 1 megasample analog to digital converter. But in some cases, like let's say optical payloads or satellite sensor signal acquisition systems, finer resolution is needed. And we see that customers more and more that this finer resolution is really a requirement. And this could be because they need to monitor temperature more accurately, or they need a finer resolution for position feedback. If that's the case, we can offer our ADS 1278, which is 24-bit delta sigma 8-channel simultaneous sampling ADC, or ADS 1282, which is also delta sigma converter, but the resolution is even higher and goes up to 31-bit.
Right. And for such high resolution data conversion, it's also very important to provide a super clean reference voltage to the ADC. And interesting implementation I want to mention here could be like using a shunt reference, such, for example, a LM4050 QML-SP, followed by a so-called composite amplifier, where you could use the high impedance amplifier LMP7704 again, as we mentioned before, and combine that one with the LMH6628, which is a very fast and super low noise amplifier. And such configuration kind of combines the best out of two worlds then for you.
Yeah, fully agree, Michael. And let me add something else here. So another important aspect that we need to think about is also to fit the input signal to the ADC with the best possible quality. So we need to think about parameters like noise suppression, amplitude, and linearity. So we at TI, we developed fully differential amplifiers, such as the LMH5485. And this device provides to customers very high unity gain bandwidth for best possible linearity, suppression of any common mode noise due to the differential architecture. And on top of this, this device also offers a very low current consumption of only 11 milliamps. There is also another important point to mention here, in case the input signal is coming from a passive sensor. So in other words, the signal source is high impedance in nature. You will need to add also a buffer on top. And this is because the FDA, so the fully differential amplifiers, do typically have only a low input impedance. And for this case, LMP7704 could be again a very good choice. Now, for active sensors, like for example, CCD sensors in imaging applications, you could feed the signal directly to the differential amplifiers like the LMH5485 we talked about.
Right. And yeah, as Adrian explained, with this, we have built now a great data acquisition system for all kind of specific use cases. But now let's also talk about the second item that Adrian introduced in the beginning, was about the design adaptability. So what we mean with this is that designers typically want to prepare their solution for the different orbit requirements. So in a bit simplified way, just develop one board, one design, and then simply adapt it by only exchanging individual components according to your mission requirements. And to help that, Texas Instruments is offering the whole range of space-graded products. Like an example could be here the previously mentioned ADC 128 S102-SP, which is also offered as an ADC 128 S102-SEP. As said, the SEP stands for the Space Enhanced Plastic, which is the version with the lower radiation performance. In this case, we always say a minimum of 30 K-rad and 43 MeV. And it comes in a plastic package, opposed to its ceramic packaged sister device, which has the 100 K-rad and 120 MeV, fairly high radiation hardness, which you need then typically in your higher orbit missions.
By the way, let me add something. So the LMH 5485 I just mentioned before does also exist in SEP version. And there is also much more, but I think the important point here to mention is that the complete data acquisition system is covered by Texas Instruments in SP and also SEP flavor.
Right. Okay. Yeah. It's amazing to discover, how much is involved in these decisions that need to be made at the at this level in order to create an effective data acquisition system and overcome these typical challenges. And very pleased you touched on both performance and adaptability, because as mentioned earlier, I think both things are becoming so much defining so much of the decisions that need to be made by satellite designers and satellite operators, and ultimately they are related to the business cases of the end users. So that's great. And just to remind the audience again that we will be linking to all of the products mentioned in this audio, so you'll be able to find out more information about those. Now, so we've talked about how to develop a really high performing data acquisition system, and you've mentioned how it would be adaptable to different areas as well. However, obviously in space, things don't always go quite as planned, and there are data acquisition system and the components that are in it will be interfacing or could potentially be affected by lots of the other systems in the satellite or the behavior of the satellite itself. So how good are the fault detection and fault tolerant systems being used today in some of the applications that we've discussed? And do you see there being, plenty of room for improvement in the next generation of missions or missions services that are in development?
Yeah, that's very interesting. So in space developments, obviously, there is a great focus on making the technology highly robust against a harsh environment, right? But there is always a chance that something breaks in the system. And it could be a fatal single event effect, or it could be even a generic component failure. So now designers, they add a lot of monitoring and diagnostics capabilities into the system. And they are also trying to develop recovery strategies, such as controlled power off or of the affected system to switch to the redundant component, for example. But like in every industry, the circuits get more and more complex with every new generation of the products. This means, in other words, an exponential growth of potential failure mechanism, right? So designers must make sure really that the failure scenario is properly identified, understood, and its impact is mitigated. Now, components with integrated fault detection features can bring very high value on this topic.
Right. Yeah, maybe I could add here an example on that one. And out of the power management, here's the TPS 7H 4001. This is a red hard 18 amps synchronous step-down converter. And that one has several protection features like the under voltage lockout, overcurrent protection, over voltage protection, or thermal shutdown. And the great thing about having those things integrated is not only the PCB space savings and also the aspect of, it is also the aspect of easy to use in terms of dimensioning the design margins and thresholds.
Sorry, Michael, can I just ask, are those four the most common sort of failures that would need to be accounted for?
I would think these are common challenges in power designs, that you fear a too high current, a too high voltage, obviously, but also the too low voltage because you cannot turn your transistors on properly anymore. And of course, as a result of whatever happens, a thermal issue may arise, and you need to, at that as the last resort, have to shut it down before your semiconductor would die. Yes.
Okay. Yeah. Sorry. Yeah. Sorry to interrupt. Yeah.
No worries. No, thanks. Glad to clarify. Yeah, I think this dimensioning, right? This is what people need to get under control, and you have to be tight enough, right? But you also don't want to be too loose, or you have to kind of be loose enough because otherwise you get a lot of false alarms, right? If you overdo it. And this is not a trivial task to define the right threshold, because you must consider also the right temperature range and also the drifts of the component parameters over time as you're permanently exposed to this high radiation that makes kind of, it turns out aging on your device as it's up there. And this is where such a device like the TPS-7H 4001, it really simplifies this task significantly and provides such capabilities in the most optimized way already.
Great example. And I can even add another interesting example, and that's the TPS-7H2211. This is our eFuse solution, or in other words, integrated load switch. And this device comes with a voltage range of 14 volts and 3.5 amp current handling capability, and provides also additional features like reverse current protection, over voltage protection, or configurable rise time to minimize the inrush current, so-called soft start. And you can place this device into the power tree, for example, to protect any circuit downstream, or it could also be used as a switch between redundant components or modules in the system. And there is also a sister device called TPS-7H2201, which comes even with a programmable current limit, trip, and retry capability.
Right, Adrian, yeah, great examples. Thanks for bringing them up. Let me also add one from the digital side, or two. As with the typically more cost-sensitive LEO constellations, there's also this trend towards MCU-based implementations, as the radiation-hardened FPGAs are typically very expensive. Customers look here now for alternatives. And now overall, whether such digital systems are FPGA-based or MCU-based, the topic of fault detection and fault mitigation becomes even more important here. It has to do that just these large memories and larger digital circuits just have an increased risk of an error caused by radiation simply to their larger size and higher complexity. And accordingly, the semiconductor process technology must be improved here for the best possible radiation hardness. Here an example, the MSP430 MCU is based on FRAM memory technology, which is much more robust against radiation than the traditional flash and SRAM technologies used in most MCU products on the market. Or another approach is from the TMS570. That one here offers a very strong diagnostic and fault detection and fault mitigation capability. This architecture is really a grounds-up functional safety design. It has its heritage from the automotive space and was really designed in accordance to the ISO 26262, the functional safety standard for automotive. Now, maybe at first glance, you may wonder if an automotive safety concept is really applicable to what we need in space here. But let me assure you, it really makes sense, as all these functional safety standards, they pursue a very similar objective, which is the freedom of unacceptable risk. And this freedom of unacceptable risk is probably also exactly what we want to do and accomplish for our space missions.
Yeah, that makes sense. I was just going to ask, for clarification on that. I mean, I had visions of Elon Musk's Tesla in the Starship, so fully understand. So there's a lot that goes into it. I mean, you've just covered a whole variety of topics just on the fault detection side of things and diagnostics. When you need to consider the individual fault, identification and mitigation, performance of the components, how the components are even assembled together, how tightly they are packed, things like thermal effects or electronic effects between components, and obviously their, as you mentioned, their performance over time, the drift in the parameters, the ability to insert specific fault switches, fault mitigation switches at different parts of the power tree. And then the digital side of things as well. There's so many factors and variables that go into these decisions. And I wonder, are there any tools or methods you might suggest people could use, designers can use to like more quickly evaluate the different architectures and make decisions? I mean, particularly when it comes to achieving their original design goals for acquiring data in certain missions.
Yes, yeah. There are several tools and methods we can offer. On the one hand side, to accelerate the customer decision process, but also to predict the achievable system performance. So, and I think one very well-known tool on the market is the design and simulation tool PSpice, right? Texas Instruments is offering a free version of PSpice for customers. And in addition, we are also releasing unencrypted SPICE models for our components, and those are available directly from ti.com. So with that, customers can, for example, model the complete input stage of the ADC and, for example, compare different configurations. And after the proof of concept is successful and they decided about which way to go, we can offer our evaluation modules or reference designs to the customers. And those are also available very often directly from our TI store. So with this kind of support, really real performance measurements are possible. And if needed, the system can be modified and adjusted to reach the expected performance.
And I assume you can model then different conditions and different applications.
Correct. You can change and adjust to your specific needs.
Brilliant. Okay, makes sense.
Right. Yeah, and if customers want to complement their knowledge or seeking for ideas, solving design challenges, I can recommend to check our E2E forum. This E2E forum, there are engineers both from TI and from our customer base, and they discuss possible solutions there. And in addition, there's also TI's webpage where we are offering thousands of application notes and white papers for very wide topics. And in order to find information about space application, customers can then also visit the application page for space via www.ti.com/space and review specific application pages, like, for example, the page for command and data handling or for optical imaging payload, and there are many more. By visiting our reference design page and selecting space again, customers can find complete reference designs according to their needs. Maybe a good example here is our reference design for satellite health monitoring with several implementations for current, voltage, and temperature monitoring, and all those really provide an accuracy better than 1%. Such design, and this one in particular, is available under the TIDA-010197. And here customers get access to the complete design guide. The design guide itself includes the test results. It also includes explanations on the component choices and also on how the design was configured, so customers can quickly adapt to their needs. And of course, we also provide here the full design materials like the schematics, the bill of material, and also the Gerber files.
Something else came to my mind, Michael. If you're talking about this, let me add something else. If someone is really looking for ideas, I can really recommend to look our spacecraft circuit design handbook. This is available from ti.com, and this provides sub-circuit ideas that you can quickly adapt to meet your specific needs. And there are different circuits presented as a definition by example. And this document includes step-by-step instructions, like a recipe. And there are also formulas enabling you to adopt the circuit to meet your design goals. And in addition, all the circuits are verified with simulations.
Okay, brilliant. We'll include links to all of those resources you've just shared in the show notes, obviously, to help all the readers out there. I think part of our mission at satsearch has always been to open up the information in the industry to more people from as many companies as we can, and to try and democratize access to that information and just help bring forward the entire industry in that way. And I think there are now so many missions that can be analyzed and relied upon to give people a better start when designing new systems, subsystems, circuits, missions, whatever it is. So it's great that at TI you've also invested in making that information available to people. I think there's no need to start with a blank piece of paper anymore when there's been so many CubeSat missions and missions of all levels. So that's fantastic. And like I say, we'll share all of that with the listeners. I think, finally, we've touched on, well, pretty much all of the technical topics, and to bring it kind of back to looking to the future, because we see there's so many options out there now to optimize the data acquisition systems. But thinking more generally about how trends are moving, and we talk about it all the time, the importance of swap-C budgets, size, weight, power, and cost, how these trends are moving, how these trends are changing in the next 3 to 5 years when it comes to data acquisition systems in space applications, particularly, as we mentioned, with the increased use of high data rates. What is it that designers need to watch out for? What's coming online that they can access, or what potential issues are there that they need to be thinking about as the industry progresses?
Yeah, that's a very good question. So obviously, one trend we see making very big impact on size, weight, power, and cost is the availability and use of devices in plastic packages. Traditionally, as you probably know, the QMLV devices are in ceramic packages, and those are physically larger and heavier than the more commercial plastic packages today, right? So we at TI are working with our customers, space community, and government agencies such as the Defense Logistics Agency, DLA, or European Space Agency, ESA, to create standards that will allow for use of plastic packages and substrates in space applications. So the first development and really start of this process was the introduction of our radiation tolerant space EP portfolio. This was really an answer to customer needs, looking for a solution for the higher volumes of LEO satellites or new space. And the challenge was to find a solution that was not only low cost, but also smaller size, lower weight, which is obviously reducing launch cost, and meet the low radiation requirements of the LEO orbit. And if you think about this, plastic packages were a great choice because we could really leverage the scale of the semiconductor supply chain and at the same time reduce cost and provide smaller overall solution. So in our space EP portfolio, we now have 20 devices in production or sampling, with even many more in development.
Yeah, and as the industry became more accepting of plastic packages, we also noticed the need for devices with plastic packages that really meet the red hard requirements. And so full space devices, what currently is only available in ceramic packages. So TI worked with the DLA again to develop the new QML Class P standard and then also work towards updating the QML Class Y standard, which should be ratified by the end of 2022 or early 2023. We'll see. And similarly, also ESA has developed the new ESCC 9000P standard, which actually is closely matching the QMLP. And these new standards allow for plastic encapsulated package in the case of QMLP or organic substrates in the case of QMLY. We already have devices in development to meet these new standards. Since the plastic packages can be much smaller, they also have an added benefit of allowing for higher performance devices and higher performance in several ways. So maybe just let me give 2 examples. Like the one is where overall, right, the smaller package means you have shorter bond wires or even no bond wires for flip chip devices, and therefore less parasitic inductance and resistance. So on the examples on power, right, here, this means you can make a more efficient power device, which then potentially reduces the need for any additional thermal management in the satellite. Or in the case of RF, right, it allows you to run things at even higher frequencies that way. And the other benefit is since the development time for plastic packages is much shorter, as this is much closer to what we do in commercial area, we are able to release more modern devices to the market and quicker, allowing for ultimately more innovation in space.
Yeah, that's totally true, Michael. We are continually releasing new, more modern and more efficient devices into market. Let me give you an example. We already talked about the analog to digital converter ADS-1278. This device operates at less than 20 milliwatts per channel. So, and similarly, our microcontroller, the MSP430FR5969, with even 16 12-bit ADC channels integrated, consumes less than 9 milliwatts in active mode and less than 0.7 microwatts in shutdown mode. Another example, our TMP461 is a fully integrated digital temp sensing solution. This device is operating at approximately 1 milliwatts for conversion and 50 microwatts in standby mode. This device gives satellite designers the flexibility to pack more and more into the same power envelope on the spacecraft, compared to what was possible in the past with older and more discrete circuits.
Right, fantastic, which for so many designers is the goal. And as we're seeing, new innovative payloads being developed that needs a certain architecture based around them, this is the sort of design considerations that will need to be increasingly made in order to cope with that. So thank you very much. I think that's a great place to wrap up. I think you guys have shared some really useful information today. I think for anybody out there looking to optimize their data acquisition system, it's very clear from that the component level and circuit level that the TI's experience with and product lines that have precision analog signal chain solutions, give you the authority to speak on the subject and covered many of the different factors and problems that can crop up, and I think that's really useful. And then obviously we've looked at full system solutions from actual data acquisition to processing and response generation, and obviously everything that goes into the whole monitoring and diagnostics. I think that was very interesting for people to consider. It's not just about how the system is put together and optimized in the clean room. It's about how it works in space and deals with problems on orbit. And finally, as I've mentioned when we talked about it, I think the work that TI is doing to help designers make better decisions or start further along the process when they're doing their own designs are really useful, and we'll share the links to the various resources you have to help people deal with the compromises that are forced upon them by the environment of space, but by their own SWaP-C budgets as well. So I'd like to thank both of you for spending time with us on the Space Industry Podcast, and really appreciate all the insights you provided today.
Yeah, thank you very much.
Thank you. Our pleasure.
Great, thanks. And to all our listeners out there, thank you too for spending time with us on the Space Industry Podcast today. As mentioned, we will have lots of links and resources for you in the show notes about Texas Instruments, and you can find out more about all of their products and innovations and the information they provide at those links. So thank you very much, and we look forward to seeing you next time. Thank you for listening to this episode of The Space Industry by satsearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth, behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.